Hello, AP. This is Mrs. Sargent, and we're going to finish up the Chapter 8 notes and then just one section of Chapter 9 that we need to discuss. So this is starting on page 12 in your note packet. At the top, it says molecules with 5 or 6 electron domains around the central atom have a molecular geometry on either a trigonal bipyramidal, which has 5 electron domains, or octahedral, which has 6 domains in the electron domain geometry. Now, I'll be honest with you, when I was looking at these notes, I was trying to figure out what the lines that I had on these pages were for. I've already typed the answers in on those lines, so you won't have anything to fill in until the very bottom of this page, but you might want to add in some additional notes as well. So one of the things is that when you have your molecules that have the 5 or 6 electron domains, there is something that is called axial and equatorial positions on the molecule. So here I have a diagram of a trigonal bipyramidal. And so the way that I think about the axial and equatorial positions is I think about our Earth and how there's a north and a south pole and there's an axis. Those go, top and bottom of the globe as you look at it, and then the equator cuts straight through the middle. So similarly, these atoms that are positioned kind of cutting straight through the molecule are the equatorial atoms, and this one over here is also an equatorial positioned atom. And then the axial, if you think about like the north and south pole axis, so this would be an axial atom. And then this would also be an axial atom as well. So that's just some terminology that sometimes they might refer to in a molecule. The hydrogen that's in the equatorial position, or the chlorine in an equatorial position, or something like that. So then because the domains from the non-bonding pairs exert greater repulsions than those from the bonding pairs, non-bonding domains always occupy the equatorial positions in the trigonal bipyramidal. So what this is saying is if you have lone pairs, those lone pairs are going to be found here in the equatorial positions. You're not going to find those in the axial positions, because remember, trigonal bipyramidal can also refer to the electron geometry, not just the molecular geometry. So just keep that in mind. The molecular geometry most common shapes. This is something that you do not have in your notes packet. I put this together and I felt like it was important stuff to keep in mind. So the most common shapes that we deal with are as follows. Most of the time we're going to have tetrahedral. Sometimes we're going to have pyramidal, like a trigonal pyramidal or a trigonal bipyramidal. Your bent, your linear, and your trigonal planar. So it's to your advantage to know some of the common examples from these shapes. So let's just talk about a few of those. Tetrahedral, you have your methane, CH4 is a tetrahedral example. For trigonal pyramidal, your ammonia, your NH3 is an example of trigonal pyramidal. Bent, most common bent shape is your H2O. Why I'm drawing it like this, I don't know. Kind of linear. CO2 is a common example of a linear shape. And then, I'm blanking on an example of trigonal planar right now, but you can look back through your notes. We've talked about some of those previously. Let me see if I can see one that I know how to draw off the top of my head. CO3 2 minus is a trigonal planar. The ideal bond angle between the center or the central atom and the other atom should be noted. For linear, it's 180 degrees, tetrahedral 109.5 degrees, trigonal planar is 120 degrees. So these are like some of the most common bond angles that you will work with. It would be great to know what these are. And so that is just going to help speed up your process. So due to the lone pairs of electrons on pyramidal and bent shapes, the ideal bond angles are going to be less than 109.5. So your typical tetrahedral is exactly 109.5. Even though ammonia has an electron geometry of 109.5 degrees, or not 109.5 degrees, because it still has the electron geometry of tetrahedral, but its molecular shape is trigonal pyramidal. This lone pair takes up more space than what a bond does. And so the bond angle, the angle between the bonds, is 107 degrees. And then with water, still has a tetrahedral electron geometry, but again, because we have lone pairs, these two lone pairs give a less than 109.5 degree angle between these bonds, and so it's 104.5 degrees. Most of the time your justification is because the lone pair takes up more room. That means that the bond angle is going to be 109.5. I have seen questions on the AP exam ask in like a larger molecule why the bond angle wouldn't be one of these three, and it usually is related to the lone pairs taking up more room, and so it is less than what is expected. So molecular geometry, electron repulsion. In general, multiple bonds repel more than what lone pairs do. So here, this is a trigonal planar shape with your carbon with 2 chlorine and 1 oxygen. But the double bond here takes up more space than what a single bond would, or what a lone pair would. And so you have a greater bond angle here, and that means that these 2 chlorines are going to be closer together. Okay, so this is picking back up in the middle of page 12, we're talking about shapes of larger molecules. Now, this is something that I have seen multiple questions on different years' exams talking about these concepts that we've looked at these shapes in the smaller molecules, and now we're taking that and we are applying that to a larger molecule. So I would pay attention to this. So this is acetic acid, CH3COOH. There are 3 interior atoms. There's 2 carbon atoms that are interior, and then 1 oxygen atom that is interior. So we assign the molecular and the electron domain geometry about each interior atom separately. So this first carbon over here, we have the 3 hydrogen bonded to it, and then the carbon is bonded to another carbon, so it has 4 electron domains. So that first carbon has a tetrahedral shape to it. This is both its molecular and electron geometry. And the second carbon, if you look at it, it's bonded to that first carbon, it's bonded to the interior oxygen, and then it's double bonded to this exterior oxygen. So that means that it has 3 electron domains around it. So the geometry around the second carbon is going to be trigonal planar. And then I'm just going to label this 3 for the interior oxygen, since this is the third one we're talking about. Okay, so this is one that confuses a lot of people. So the oxygen here, it only has 2 electron domains with the bonded atoms. But if you notice, the molecule is kind of showing us what the shape is. And so because it has this bent shape, that means that there are 2 non-bonded electron pairs. So the electron geometry is tetrahedral, where the molecular geometry is bent. And so that's something that you kind of have to think about. Is the oxygen, is the octet satisfied with those bonds? Well, if it's not satisfied with those bonds, then that means that we have to have non-bonded electrons or lone pairs. So you kind of have to think a little bit more than what is shown in that picture. So at the bottom of page 12, there is a practice problem with another larger molecule. I will post the answers to those at a later date on Canvas. Now, I do have a little bit of notes regarding the molecular shape and molecular polarity. So we talked about polarity at the beginning of chapter 8, and I'm not honestly sure why the textbook chose to put it at the beginning before we reviewed Lewis structures and before we reviewed molecular shapes, but that's what they did. I did add in a few notes here, so you might want to just jot these down on a separate sheet of paper. When there is a difference in electronegativity between 2 atoms, then the bond between them is polar. So we've talked about that previously, looking at the location of the elements on the periodic table and thinking about the electronegativity difference between the atoms. So it is possible for a molecule to contain polar bonds, but that it is not polar. So for example, CO2, each of these are a polar bond. So the more electronegative atom is going to be oxygen. So it's showing that the dipoles are pointing towards the oxygen. That means that the electrons are being pulled closer to the oxygen. But however, since you have this dipole going this way and this dipole going that way, and it's the linear shape, those dipoles are going to cancel each other out. And so there is an overall no dipole moment for this molecule, and that this molecule is nonpolar. In water, the molecule is not linear, and the bond dipoles do not cancel each other out. So therefore, the water molecule is nonpolar. We still have that electronegativity difference between hydrogen and oxygen, and so the bond dipoles are both pointing towards oxygen. But see, since the dipoles are pointing towards each other versus away from each other, this is a polar molecule, and the overall dipole moment is drawn here, showing that overall we are pointing towards our oxygen atom for that dipole moment. That's a really bad job of highlighting, so we'll just fill this all in here. But this is the overall dipole moment in the water molecule, which is important, polar, water being polar, because then it can dissolve polar substances. So here are some common shapes of molecules, and looking at how the shape and molecular polarity play into each other. So linear with two atoms, most of the time, if these are two different atoms, it's going to be polar. If you have two of the same atoms, it would be nonpolar, like if you had H2, that would be nonpolar. But two different atoms typically is a polar molecule, and chlorine is more electronegative than hydrogen, so it the dipole goes towards chlorine. Now for BF3, fluorine is our most electronegative atom on the periodic table, and so these dipoles are pointing outwards. Since this is symmetrical, and these dipoles are all pointing out towards the fluorine, they're pointing away from each other. This molecule is nonpolar. So typically your trigonal planar with similar bond dipoles is going to be nonpolar. You do need to say that it's more than just the symmetry of it, but saying that because the bond dipoles are pointing away from each other, then it is overall, they're canceling each other out, and it's nonpolar. Similarly with CCl4, all of it's symmetrical. All these bond dipoles are pointing away from each other, so they're canceling each other out. So your tetrahedral are typically nonpolar. And then in H3, this is trigonal pyramidal. And you can see that each bond dipole is pointing towards the nitrogen atom. And so your overall dipole moment is going to be pointing towards the nitrogen. And then an example of a tetrahedral that is not symmetrical, has one atom that is different, CH3Cl. This is going to be polar, and the dipole moment is shown here, going towards that chlorine atom. So continuing on page 13, looking at chapter 9, there's just one section in chapter 9 that we need to talk about, and it's really just pages 13 and 14 in your notes. So 9.1, when drawing Lewis structures to explain bonding, we have been using the localized electron model of bonding. So what this assumes is that the electrons stay with or close to the atoms from which they originated. That's where the bonds are formed, and they overlap of atomic orbitals. So because there's this overlap of atomic orbitals, this model needs to be developed a little bit further to explain experimental data. So we're going to use methane for an example. Methane is CH4. Carbon has one 2s and then two p orbitals available for bonding. And so hydrogen has one 1s orbital that is available. So what these available orbitals for bonding come from, where are those valence electrons located at? So hydrogen, it's the 1s because it only has the 1s orbital. Where for carbon, 1s, 2s2, 2p2 is where that's your electron configuration. So we could imagine that one of the bonds in methane would be formed from the overlap of hydrogen 1s and the carbon 2s orbital. And the other three bonds would be formed from an overlap of the hydrogen 1s orbital and the carbon 2p orbital. This would make two different kinds of bonds. So I know that this sounds really confusing. I'm going to break this down for you. But I'm just kind of telling you where all this information came from and why they're suggesting a different model. So the experimental data shows that all four bonds are identical. So how do we resolve this? If the bonds instead were an overlap of the hydrogen's 1s and a new kind of orbital from the carbon, then the bonds would all be equal length. Well, so this new orbital from the carbon is created by utilizing carbon's 2s in all three of its 2p orbitals. These orbitals are blended together, okay? So that it's not going to be just a 2s, it's not going to be just a 2p. And when they're blended together, they're considered hybridized into a mixture that produces four orbitals that look a lot like p orbitals with a hit of s. So here's your s orbital. Here are the three 2p orbitals. So now hybridization blends these together. They look like a lot of your p orbital and then just a hint of this s. And when all three of these, or all four of these orbitals, fit together, they look like this. And you get this tetrahedral arrangement. So that blending that we talked about, these are called sp3 orbitals to indicate what they are made from. The hybrid sp3 orbitals each overlap with a 1s orbital from each hydrogen atom, and it makes four identical bonds that have 109.5 degree bond angles, and these overlapping bonds are called sigma bonds. So whenever atoms have four effective electron pairs or four electron domains, they have an sp3 hybridization. Even if they are unshared, like in H2O, that oxygen is still going to have four electron domains in our NH3, which is also going to have 4 electron domains. The electron pairs, both bonding and non-bonding, have that tetrahedral arrangement. So this again is just kind of showing the CH4, and then here's the NH3, and the lone pair is up here. Okay, so now I'm going to try to simplify all of that crazy information in a little bit simpler terms, but I did want to show you where that came from. So a hybrid orbital is simply a mixing of different orbitals together to form a hybridized orbital. We need the concept of hybrid orbitals in order to explain the molecular shapes. So this is where we're going to keep it simple. When you mix a certain number, that's what your N is, that certain number of atomic orbitals, you're going to get that same certain number of hybrid orbitals. So if you mix 1 s orbital and 3 p orbitals, you will get 4, because you had 1 plus 3, that equals 4, and then sp3, because s, you had 1 of those, and then p, you have 3 of those. So you have a total of 4 sp3 hybrid orbitals that all have exactly the same energies. So we still have the same total number of orbitals, but we've just combined the s and the p into sp3. So this chart, it shows you what the hybrid orbital set is here. That is what is the hybridization. I do have a few examples here for you. To the left of that table, it says the number of electron domains. So your hybrid orbital set for a linear geometry, this has 2 electron domains, which means you're going to have 2 sp hybridization. Then this has 3 electron domains, and so that's going to give you 3 sp2, and then 4 electron domains gives you 4 sp3. And these are the main ones that you need to know for the AP exam. I'm going to just tell you what these other 2 are since we have them here. This is 5 electron domains, and the hybridization is 5 sp3d. And then this is 6 electron domains, and it is sp3d2. So I'm just going to write what these hybridizations are a little bit bigger for you to see those. So thinking about the number of electron domains on an atom will indicate the hybridization needed. So when we look at this molecule, C2H4, and we look at each carbon. So each carbon has 1, 2, 3 electron domains. So the hybridization must be sp2. And so it's going to have 3 hybrid orbital domains as well. So this is that same information that we just looked at the bottom of the last slide. So when you have overlapping of orbitals, so we had a little bit of overlapping coming in here. The bonds are going to happen when 1s orbital from hydrogen overlaps with the orbital from carbon. So this overlapping that we're talking about comes in two varieties. So the first variety is sigma bonds. The electron density lies on the axis between the nuclei. So these are just like that. Those electrons are lying straight on the axis between the two atoms. So all single bonds are sigma bonds. So you have sigma, 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 and then the pi bonds, the electron density lies above and below the plane of the nuclei. So here's kind of our molecule separated out into the sigma. So there is also, in a double bond, it consists of one sigma bond and then also one pi bond. So we have 1, 2, 3, 4, 5 sigma bonds in this molecule, and then we have one pi bond because it kind of looks like it makes the pi symbol above and below. But this is just one pi bond altogether. A triple bond has one sigma bond, and then it also has two pi bonds. So often the p orbitals are involved in the pi bonding, and they come from unhybridized orbitals. So in this molecule C2H4, we have 5 pi bonds that are formed from the overlapping of the sp2 hybrid orbitals on carbon, and the pi bond is formed from the unhybridized overlapping of the p orbitals on each carbon. So another example, this is actually the example on the right-hand side. You have CH2O. So your molecule, if we were to draw this out, we would look like this. And so we're going to have a sigma here and a sigma here, and one of these are going to be sigma, and then we're going to have one pi bond. So C and O both have sp2 hybridization, and each has an unhybridized p orbital to make that pi bond portion of the double bond. Then with C2H2, we also have we have 3 sigma bonds, and then we're going to have 2 pi bonds because of that double bond. Or I'm sorry, the triple bond. I think I'm going to skip over these 2 slides. I must have recopied slides into here. So, okay, so there are some examples where it has you draw the Lewis structure. Think about the hybridization, the bond angles, the molecular shape, the sigma bonds, and the pi bonds. So why don't you pause the video and give these 3 examples a try, and then unpause it, and we'll come back and take a look at these examples. Welcome back. So we have sp Cl5. So Sb goes in the center, and then you're going to have 5 chlorine atoms that are bonded to it. And then so antimony has 5 valence electrons, and then we have 5 chlorine atoms that each have 7 valence electrons, so 5 and 35 gives us a total of 40. We have 10 electrons involved with the bonding, so that leaves us with 30. Each of these chlorine atoms are going to need 6, and that 6 times 5 is 30. So your Lewis structure is going to look like this. So hybridization on your antimony atom. So it has 5 electron domains. So this is one of those more advanced hybridization. This is sp3 D for the hybridization. The bond angles on this, let's come back to that. The molecular shape is trigonal, bipyramidal. And so the electron, or the bond angles, are 120 degrees and 90 degrees. So sigma bonds, everything is single bonded. We have 5 sigma bonds and we have 0 pi bonds. Then with NO3, 1 minus, so nitrogen goes in the center, the 3 oxygen atoms bonded to it. So we have nitrogen has 5 valence electrons. We have 3 oxygen atoms that have 6 valence electrons. So 18 and 5 gives us 33, or 18, 23. Plus 1 gives us 24. And subtract your bonded electrons, that is 6. So you have 18 that remain. Each oxygen is going to need 6 and nitrogen needs 2. So you're short 2. So you're going to need to double bond one of these. Subtract 2 leaves you with 16. And so then you're going to have enough, and you're going to be able to put the dots on your Lewis structure. Remember, since this has a charge on it, you need to put it in brackets and put the charge on it. So nitrogen has 3 electron domains on it, so that's going to give it a hybridization of sp2. This is a trigonal planar shape. And the bond angles are going to be 120 degrees. Sigma bonds, we have 3 sigma bonds and 1 pi bond. And then with CHCl3, carbon goes in the center, 1 hydrogen, 3 chlorine surrounding it. So carbon has 4, hydrogen has 1, then you have 3 chlorine times 7 valence electrons. So this is 21, 22, 26. Subtracting the 8 that you have bonded, that gives you 18. Carbon and hydrogen are good. Each chlorine needs 6, so that's your 18. So your carbon has 4 electron domains on it, which is going to be a hybridization of sp3. Your bond angles are going to be 109.5 degrees because it has those 4 electron domains. The molecular shape is going to be tetrahedral. Sigma bonds, you have 4 sigma bonds and 0 pi bonds. So hopefully you're kind of getting the hang of it. If you have questions, please let me know. So this is the structure for caffeine. So like I said, with kind of looking at molecular shape and the electron geometry, a lot of times AP exam questions have you look at a larger molecule to apply the concept to. So here, with caffeine being a larger structure, this is present in a lot of coffee and many soft drinks. The question is asking us how many pi bonds there are and how many lone pairs are in the molecule, as well as how many sigma bonds. So for the pi bonds, let's see if it'll let me do this. So pi bonds are only going to be in our double bonds. So there is a 1 pi bond, 2 pi bonds, 3 pi bonds, 4 pi bonds. So we have 4 pi bonds, and I'm going to show that I highlighted that in the yellow. And then for the sigma bonds, all of your single bonds are sigma bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I feel like I lost count, 15. But then what's tricky about this molecule and how they show like the CH3 here and here and then the CH, that actually means that this carbon has 3 hydrogen coming off of it. So that would give us 3 more there and 3 more here and 1 here and then 3 here. So let's count these up because I kind of lost track of my counting. We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I know that there's 25. I just am having trouble counting right now. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's all of the outer. And then 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There we go. Now I can count. So we have 25 sigma bonds. And that is what I highlighted in the red. So hopefully that gives you an idea of how this applies to your larger molecule. Now, if on your note packet you had a page 15, a lot of that is just repeated information, so you do not need to worry about page 15. I just crossed mine out. Please, if you have any questions, please don't hesitate to email me or text me or whatever. the best way of getting a hold of me would be. Thanks. Have a great day.